Okay, so what we are going to discuss today is uh, an application of neural networks for a classification problem. As we have seen, the general theory, if you want to use neural networks for classification, then we know it's something like this, that neural networks, they create many separators. uh, these separators are each neuron is a kind of separator. It has a equation of line, which is basically in general form written as W times your input X, right? Where W is the matrix, which is the weight matrix, and X is your input vector. It could be input vector or basically uh, the vector obtained from the previous layer. So this is not necessarily the feature input, but it could be any input to the neuron, maybe intermediate input. So this neuron is represented by this, and then plus some bias, like W, like this mx plus c. So this is like m. So this is like your m, and this is like your c. So, and this is equal to 0 for the line, and it is greater than 0 for one side of the line, less than 0 for the other side of the line. And then you apply a non-linearity. The non-linearity is some function f. It could be a sigmoid function or a rectified linear unit, etc., but some non-linearity. And then this is the output of one neuron, and then you have multiple neurons in a layer which take the same input X and apply different W's to that and different B's to that X. Then this output of this layer, or basically multiple outputs of each neurons, can further go into another layer of neurons, and in this way we can have multiple layers of neurons. And but finally our output should be a kind of probability of each class, right? Finally my output is a kind of probability whether my class is A or B. I think it was there in the other lecture, right? So here we saw how the output is a probability, that probability of class yi given my input x. So for example, for the simple example in our lecture notes, you have seen probability of which flower it is given the height and width of the flower. So if the width of the flower is this, height is this, that is a x, then whether it is a rose or a lotus or a jasmine, so these three classes were there. And so this was the basic theory, and yeah, and we discussed, we use different kind of loss functions, etc. So today we are going to discuss one practical problem here, like this. This is on mnist dataset. Mnist dataset is basically the input is an image of size 28 cross 28, and each pixel can be binary 0 or 1. Like each pixel is either 0 or 1. For example, in this image, the white ones are all, let us say, zeros, or black ones are the ones, or it could be other way also. White ones are the ones and black ones are the zeros. Anyway, so this is just uh, the kind of input which we receive. And you see, uh, one image is input at a time, and the output of my classifier is I have to tell which digit it is out of the 10 digits, starting from 0 all the way to 9, which digit it is. So the output is a label. Input is an image, output is a label or the class out of 10 classes. So the problem is to classify the handwritten digits. This is like image of a handwritten digit into one of these classes, 10 classes. Each image is 28 cross 28. Now we have to, let's see first what is the data set. Our data set is the mnist data set. It is a very common data set available online, and our standard libraries such as Tensorflow, Keras, etc. they come with this dataset. Basically, this dataset is already available in these libraries because it is a very common dataset used for uh, building our algorithms or testing our algorithms, like a test base. So what we are doing is we are using TensorFlow for our neural network library, and within TensorFlow, Keras is a kind of uh, uh, utility or a module which has got uh, different kinds of networks already implemented. So if you want to use some existing neural network like multi-layered neural network or recurrent neural network, convolutional neural network, then you can simply pick one from Keras library and just use it. And then we have got our data set mnist. So first of all, I am loading my data. I load my data means I have got four variables: train samples, train labels, test samples, test labels. So my train samples contain all the inputs for training, and my train labels contain all the desired outputs for training. Similarly, test samples and test labels are correspondingly X and Y for testing. Now what we do is we let us see what are there in these variables.
Excuse me, sir.
Yeah.
Sir, what is the difference between a test sample and a validation sample? I'm not getting this.
Okay. Good question. Good question. So training data is used for training the model, and this data is it means that we know the labels for this data, right? For example, if this is my training data, then I know that okay, this 28 by 28 image is there, and I know its label. That is what I use for training, right? During training, this is available, but during test, I only have the input. I don't have the corresponding label with me, and I feed this input into my network. Network will predict a label. That's it. And then it goes to the evaluator, or means the next part of the program, which will do the evaluation. Now evaluator knows the actual label for this image, and since I have provided, so evaluator also have the estimated label for this image. So the evaluator will compare these two labels if they are same or not. If they are same, then it will say yes, you are successful. If they are not same, it will say no, this was a wrong output from your model. So this is test time. Now, what is validation? Validation means, I'll give you an analogy. Like when you do an assignment or when you are learning a course. So what you will do, you will go through the theory. That is like my training data, right? Or you will go through some solved examples. That is like your training data, right? You know the answers, so you have the theory with you from where you learn. Then you have some solved examples where question is there and answer is there, both are given to you, and you learn, okay, if this is the kind of question, then this is how you solve it and this is how you get your answer, and you train over it. Then there is an exam time where you don't know the answer, you just solve the questions and submit your answers. And then there is an evaluator, the examiner or your instructor, who knows the right answers, and they will be comparing your answer with the right answer and then giving you score. That is the test part. Now if you just read the book and go to the exam, then you are afraid that I may not do very well in the exam. So what you do some mock test. So that mock test is, okay, you hide your answers. You know answers are available in the book, but you hide the answers. You don't look at the answers. Without looking at the answers, you try to solve the question. And then whatever you have solved, then you compare it with the actual answer from the book. And then you understand, oh, see, I made a mistake. Oh, I did it correctly, like that. And so it is still the training time. It is still before the exam time, but you are doing a mock test. So validation is like a mock test where, so first you train your network and then you do a mock test on the validation data, and then you check whether I really learned something or not. If I have not learned, then go back to the training train yourself more, come back to the validation part, again do a mock test and see whether you have learned or not. And then you go to the final exam, right? So that's the thing. So you have training. It is like you are reading the book or reading the theory or what do you say, solved examples or solved exercises, right? And then you have testing time, which is like an exam. In between, you create validation stage, which is like a mock test or mock exam. So basically, where you are testing yourself whether you have trained yourself well or not, whether you have really learned it or not. If you have not, if you get a bad result in the mock test time, then you go back to your theory, understand it properly, or read it more carefully, solve some more training examples, or look at more exercises, and then again come back to the mock test. Again, do the mock test, and then again, now your performance has improved. Then, when you're confident, then you go to the test time and then you give the final exam. Is that clear?
Yes, sir. Yes, sir. Yes, sir.
Okay. So let's look at the mnist dataset. So it's very simple dataset. You have training samples. Now you see there are 60,000 training samples and 10,000 test samples. And when you say train samples, there are 28 cross 28 matrix. Basically, this matrix is 60,000 cross 28 cross 28 because there are 60,000 examples. Each example is 28 cross 28 image. And then the labels are 60,000 cross 1 because only single label is there, 0, 1, 2, 3, up to 9. That's it. You can also print these values and see what exactly these values are. So now when you look at the data is, so if you feed the data as it is into your network, we have discussed the need of data normalization, that we want the data to be in a narrow range around zero, maybe if possible, between the range 0 to 1 or -1 to +1 or -5 to +5 or -10 to +10, something like that, some very close to zero as much as possible of the order 1, so that your uh, tuning parameters, hyperparameters, etc., are very much standard and you can just work with them. But if your input data has large range, then your network may not train very well. It may go to saturation, etc., etc. So basically, it's kind of data preparation, that you bring your data to a narrow range so that standard algorithms, standard hyperparameter values you can directly use, because other people also have worked in the same range. So you can use their knowledge directly instead of reinventing the entire knowledge. And again, when you solve another problem, again you will normalize it so you can use your same network in a better way. Okay, so now so what we see is this data is, you see np.a max. This data has an upper boundary. It's bounded. It's between 0 to 255. So the lower limit is 0. So minimum value is 0. Upper value is 255, because you know that these are binary values, 0 to 1. And these are 0 to 255, basically. Means pixels are binary, but their values are 0 or 255. So you normalize it. How will you normalize? You can use mean standard deviation normalization, but here in this case, you directly know that it is 0 to 5. So you can simply divide the data with this value 255. Then all your data is between 0 to 1. Just divide with a constant number. Okay, now this is how the data looks like. You take one sample, let's say the 0th sample, and you plot it. This is how it looks like. And the label is train labels 0. So train samples looks like this, and train labels look like this. This is just number 5. Then you do, okay, data preparation. You first normalize it to between 0 to 1. So basically divide by 255, and then that's it. Now the maximum value has become 1. So that's it, just a small thing. Now you okay, so now what we do is, now data is available with us, it is normalized. Now what kind of network do we want to apply? We want to apply a convolutional neural network or a recurrent neural network or a simple multi-layered network or dense network. So in this case, we are going with a dense network. So it is simply a dense network, which means my input is a vector and output is also a vector, and the all the input neurons, input layers are fully connected layers. So like that. So what I do is I reshape my layer from 28 cross 28, which was a matrix. I converted into a vector. It's of length 784. Right now, the input is prepared. My input are all x vectors, not the matrices. These are x vectors. Each x vector is of length 784. And now come to the output side. So what is my desired output? For example, my desired output was 5. Now, as I have discussed in the lectures, that we cannot represent them, cannot represent my desired output as 0, 1, 2, 3, 4 up to 9 and then use a regression model. No, that is not what I do, because there is a reason to it, that there is no linear ordering in my classes. These classes are all kind of independent. So that's why I create a 10-dimensional vector so that each class is equidistant from the other class. Each class is equidistant from the other class. And how do I do it? I simply represent, like if you have read encoding, decoding. Encoding means you just encode your some input into some other form. So it's like an encoding. You encode your digits into one of these one hot vectors. So you see 0, 1, 2, 3, 4, 5. So the fifth entry is 1. If this would have been 0, then zeroth entry would have been 1. If this were 1, then the first entry would have been 1, like that. So this is my one hot vector. Now I will use my Keras or the basically TensorFlow to create the network. Okay, no, okay, okay. So yeah, this is that's the steps involved to do this operation. This is just you use a function called two-categorical. The input is 5, then it will output the one hot vector. So these all one hot vectors are saved in train label and test label, and the example is given here.
Excuse me, sir.
Yeah.
Sir, here, go up, sir. Scroll up. Yes, sir. Yes, sir. Sir, here we have converted a 28 cross 28 image to 784, right?
Yes.
That means one dimension vector.
Yes.
Then we have made a one hot vector corresponding to each beat,
Yes.
right?
Yes.
Then hot vector of dimension will be 10 cross 784, right?
No, 60,000 cross 10.
Okay, okay,
784 is the input size. Output size will be independent of that.
okay,
60,000 cross 10.
okay, okay, sir.
Okay, good question. So let's move on to the network now. No, okay, now we have prepared our inputs. So if you remember, uh, our model is like this. We have some function f here, and my inputs are x and y, and I want to match it to y desired. Right? I want this y to match y desired. So this x is prepared by the normalized 784 cross 1 vector. My y is simply 10 cross 1 vector, or y desired. Now I have to come to my neural network, the function, which is converting this. So my function is basically, it looks like this. It is a little bit dark. Oh, why is it dark? I don't know. I have to. I don't know how to change the color. Background color. No, it's even worse. It was an SVG kind of book, but I can put it on some white background. Let me see. Okay, let us come back to this later. So we have three layers. You can see first layer is the input layer, then the hidden layer, then the output layer. And the output layer is such that you have got 10 neurons here. So, okay, how many neurons are there in the input side? In the input side, how many neurons will be there?
784.
Yes, very good. So 784 neurons in the input side. And in the output side, how many neurons will be there?
10.
10 neurons. And in the hidden layer, how many neurons will be there?
It all depends upon user.
Yeah, it could be any number. It is a hyperparameter and we can choose the value for that hyperparameter. I can take it to be 100, 500, 1000, whatever. Generally, it is kept in as a multiple of 2, means as a power of 2, 1024 or 512 or 128 or 64, like that. But yeah, it's up to you to decide what you want to keep. Then so this thing is okay, not very crucial, not very critical, but what is critical is the output. What are we modeling with the output? So we are modeling probability of y given x. Y is a class given x, right? Where my c can be 0, 1, 2, so on up to 9, right? So this is what I want to model at the output. My output is not directly y, but probability of a particular y. C can take 10 values. So this is what I want to model. So to have probabilistic interpretation, I would like that all my y's should sum to. So I think let me just, I will say my y is equal to this probability of a class given C, where my class can be any of these, right? I would like my, say this is yc, right? Because y will have 10 values. If y is a vector, it will have 10 values. So the 0th value will be probability of the label 0. 1 will be probability of label 1, like that. So my yc, should sum to 1. C equal to 0 to 9, right? To have probabilistic interpretation. Yeah, this one is better visible here. So these output layer can have 10 values. So this is y0 is basically probability of the label 0, y1 is probability of label 1, etc., etc. So I would like all my outputs to sum to 1, and I would like my yc to be greater than 0. So it should be greater than 0, or equal to 0 is also possible in practice, in principle. So yc should sum to 1 and they should all be greater than equal to 0. Now if I simply use, if my yc is simply some w times some hidden layer, let us call it as h layer, plus b, then let's say this is cc, because the cth neuron, then this does not make any sense, because here this number cannot be constrained to be between 0 and 1 and sum up to 1. All those things are not possible. That's why we use a trick. We use a nonlinearity which is called softmax nonlinearity. So what is softmax nonlinearity? As you have seen, YC is exponential of, let us call this term as some HC. Oh, we call this as a V. Let us call this term as HC. So it's exponential of HC upon summation over exponential of H some C dash, where C dash is 0 to 9. Now you see this term, exponential is always greater than 0, right? So this term is greater than 0, right? This ensures my YC is always greater than 0. It can be 0 if HC is minus infinity, which is not exactly possible, because minus infinity is not possible in the computer. Um, and also in real life also, minus infinity is not a number, it is a concept. Now, the other constraint is sum up to 1. Does it sum up to 1? Let us try it. If I say YC sum over all C, this will be equal to sum over exponential HC. But what is the denominator? It is some C dash exponential of H C dash. Now C or C dash are just dummy variables, so they cancel out each other. This is one, right? So both my constraints are satisfied if I use the softmax nonlinearity. So that is why we use a softmax activation function, which is basically this form. And
Excuse
the
me, sir.
yeah,
Can we use the sigmoid here?
you can use sigmoid. Okay, then you have to ask the question, will it satisfy this constraint? This is the constraint which I want to finally obey. Is sigmoid satisfying this constraint? Let us look at this one. So sigmoid is always greater than 0. Yes, this constraint is satisfied. But is this constraint satisfied? Right? So yes, you can create another function. You need, if you don't want to use softmax, no problem. Create another function which can satisfy this constraint. Then it is all right. But sigmoid won't satisfy this constraint. Okay. Okay, so now let us look at how we define the network. So we use a function called input in the Keras layers, and we use this function input. We specify the shape of the layer, which is basically 784 cross 1. So this simply says this number is basically 784, and my input layer is defined. Now this input layer, on top of this input layer, I apply another function called the dense function, which okay, I am giving 512 neurons, and the activation of each neuron is sigmoid. This is the hidden layer. Now on this hidden layer, I apply the output layer, which is again a dense layer or a fully connected layer. It has got 10 neurons. This is crucial, right? I cannot change this number. This number is fixed, 10. 512 can become 1024 or 64 or 128, anything. That is allowed. But this is not allowed. This 10 should remain 10 only. You cannot change, because output size is already you have fixed as 10, fixed at 10. So now this activation function, it's a softmax function, as we just discussed. So that's it. So now our everything is ready. Input is consistent, output is consistent, all the constraints are satisfied. Now let's go to the training part. How do I train my network? So I initialize my network randomly, but then how do I train my network? To train my network, I have to use a loss function. And you have seen that we use the categorical cross entropy loss, which is basically this function, t times log p, sum over all x. So my t is a one hot vector. It's one for only a single x. Similarly, p of x is a probability function. So this will be minimum when these are exactly same, which means my p also becomes one for that particular x only. Yeah. So so my t is always a delta function. It's a Kronecker delta function. And for label 5, tx is 1 for x equal to 5 and 0 otherwise. So, and then we have defined our loss function. Now we have to train our network. We have to use the optimization scheme to update the weights of my network, the weights and biases. So what do I do? I will okay. I have to. I will now okay. Um, uh, Put my net model together. I will say my model is this model. It has the input is input layer, output is the output layer, okay, and then I am compiling this model and I am using Adam optimizer. It's a kind of gradient descent algorithm where the learning rate or the step function step size is changing with time, means as you are iterating with each iteration, the step size also is adapting itself so as to achieve faster convergence. And the loss function which I'll be using here is a categorical cross entropy loss, as we have seen above. And this matrix is basically, as the training is going on, at each epoch, it will calculate the accuracy. So, and it will calculate accuracy at the end of each epoch. Now you can use this metric to find out whether your training is going on well or not, or when to stop. For example, you want to minimize your or maximize your accuracy, then you put a constraint that I want to stop when my accuracy is maximum. For example, after some time, if the accuracy stops improving or accuracy starts degrading, then you say, no, no, stop. I think we should not go any further. Like if you remember, the concept of validation is that if after some time your validation loss starts increasing, then you say, oh, I think I have learned enough, then stop learning now. I'm now getting overfit. I'm going into overfitting zone. So in this way, you do your stuff. Then this is the function fit function. It basically it runs the actual training. So you have given the training samples, training labels. Uh, you have told it to train for 100 epochs, means 100 times the entire training data will be seen by the optimization algorithm. And you are using Adam, which is basically which creates small batches and train on the batch and then move on to the next batch, like that. It does batch wise training. So it basically takes a batch, sees what is my delta W, update the model, then go to the next batch, again compute delta W, update the model, go to the next batch, compute delta W, update the model. In this way, it trains. And so in this small batches of 200, finally, when it exhausts all the data, all the 60,000 samples are exhausted, then it will say my one epoch is over. And like that, you do 100 epochs. Now, this was if only training data is used. But now we are also saying, I want to use validation as well. It means I want to use, let us say 0.1 means 10% of the data for validation, means for mock test. I want to keep zero point 0.1 fraction of data or 10% of the data for validation. It means I do not train over. I will, like in the beginning itself, I will split my data randomly into 60. Means 60,000 are split into 54,000 and 6,000. So train on 54,000 and test or validate on 6,000. So these 6,000 answers I do not see. I do not show to my model. I only show these 54,000 answers to or the target labels to my model, so that model can learn from there. After learning, it will you do the test on this data. You don't show the answers, just find out the uh, estimated values by the model and then give it to a validator, which will compare these values with the ground truth values and give you the validation accuracy. So this is how it goes. You get your validation accuracy. So you can see your validation loss or validation accuracy is printed here. and you are saying I want to maximize my validation accuracy, and after some time validation accuracy will stop improving or it will start degrading because of overfitting. So you want to avoid overfitting, so you will stop at the point where your validation accuracy is basically maximum. So now when this training, this is the step which takes largest amount of time in any machine learning uh, run. So because this is the time when actually the model is getting updated. So you see how the validation accuracy is improving. I will not look at the training accuracy because that will anyways improve because my algorithm is good. But my validation accuracy, you see, it is 97.93%, and then suddenly it drops to 97.90%. So, but then it again rises to 97.97. It means that this is not a significant peak, but it was just maybe a plateau or something, or maybe because the algorithm is stochastic. The Adam algorithm is random. It uses randomization within it. So that is why there are some changes in the numbers, but more or less it is improving. So then it again degrades, it improves, it degrades, it improves little bit, improves, degrades. It's like, but you can see that the changes are very small. Changes are very small. Then it remains same even after one epoch. Then you again go down, then improve, then yeah, you can see it is almost like has become constant now, not improving much. 98.32, 98, it's around 98.30, 98.40, 98.40, yeah, and it is not improving at all. So basically I could have used the condition in this fit function that stop at the point where the validation accuracy stops improving, let us say for 10 consecutive epochs. Like for 10 consecutive epochs, if you see that your accuracy is not improving or your validation accuracy is not improving, then you say, okay, just stop. Why did I say 10? Because it is possible, like you saw in the beginning, that at some point of time, accuracy dropped a bit. But this was not the best point, but accuracy just dropped because of randomness, and then again it improved much better. So that is why you say, okay, wait for at least 10 times, 10 epochs, and then if you don't see any improvement, then only you stop. So like that, this will go on to 100 epochs, and you see the final result is very close. Like you can see there is no improvement in the last epochs. That is why to save my computations, I will just stop whenever I um, meet that condition of 10 consecutive no improvements. Then, okay, now I have trained my model. Now I will give this model to the evaluator. The evaluator is like the final exam or the test. So what will I do? I will take the test samples. I will feed it into my model.evaluate, and the test samples are given, and it will give me a predicted values, like these are the predicted values. And then I give the test labels. The evaluator has the test labels. This is the evaluator now, no more training, only evaluation. So evaluator has the test labels. It will use these labels to compare my results with. So you see the accuracy on the test data is 94, 98.3. Now you see this accuracy on the test data is very close to the accuracy on the validation data, right? Whereas if you look at the training data, accuracy was already 1. It has already kind of overfit or something, right? Uh, so training data, since it knows the answers, it always gives best results on training data. But on the validation data, uh, the result which it gives, they are more uh, realistic. I mean, these numbers are more realistic in the sense that they are closer to your test accuracy. That is why we use a validation data. Otherwise, see, just looking at the training data, we would have said, oh, our algorithm is perfect. But no, our validation result says, no, it is not perfect. It is 98.4% something. And then you want to see, okay, I got this accuracy, but I want to see class-wise results. Which two classes are confusing? Which two classes my network is finding difficult to identify, or which all classes I find my network is finding difficult to identify. So you can see here, these are the class-wise results: 0, 1, 2, 3, 4 up to 9. You see the 9 class is so okay. So the x-axis, or the rows represent my ground truth values, and the columns represent my estimated values. So let us look at this number 7. This looks like this is the largest number probably here. So what does it mean? It means my ground truth was 0, 1, 2, 3, 4. My ground truth was 4, but my prediction was
9.
the last one, 9. My ground truth was 4 and prediction was 9. So means 7 times my ground truth was 4, but the prediction was 9. It makes sense because 4 and 9 are quite similar in shape, as you can see in the data. You see this 4, this looks almost like 9. So no doubt that the machine makes this mistake of thinking that this is a 9, because 9 and 4 are actually very similar in their shape. So okay, this result is not very surprising for us. Now let us look at this result. This is large number 8. So what was my ground truth value?
7.
Okay, 0, 1, 2, 3, 4, 5, 6, 7. Yeah. So 7. Ground truth was 7, and my
2.
prediction was 2. So okay, so looks like 7 and 2 are very similar. Yeah, we can we can even see uh, means with my by eyeballing at the data that yes, 2 and 7. Like you see, this looks like 2. This also looks like 2. This looks like 2 with a missing horizontal
Central line.
bar in the bottom. So yeah, you can see, yeah, actually even uh, when you do data analysis, you are not very surprised that 2 and 7 are getting confused. But of course, if somebody confuses 0 with a 1, that will be a blunder, right? 0 and 1 are quite different. So 0 and 1 should not be confused. So let us look at the statistical results. Are 0 and 1 confused? Answer is no. You see 0, 0 means no time means uh, there is no example for which 0 and 1 are getting confused. That makes sense. They are quite different in their shape. But of course, it means these numbers, even if they are non-zero, they would be some small numbers. But these numbers are large because of okay, there is some justification and there is some consistency with our expectation. We expected that okay, this should not confuse, but these can confuse, and we find yes, they are actually confusing. So okay, so we can, this way we can see our data. Now I want to, I can also plot my learning history. See how my, I want to see if my model is overfitting. So let us see what is my validation loss. You see my, uh, the red curve is validation loss and loss, validation accuracy and accuracy. You see my validation loss, it decreases and then it increases. Whereas my training loss, the red one is the training loss, it decreased and then it is always decreasing. It is never increasing. While my validation loss decreases and then slightly increases. So in general, I would not like this rising curve, because this means my model is overfitting to the data, to the training data. That is why my validation results are getting poor. Like if you kind of memorize your answers in your training data, so you will not be able to solve the mock test problems very well, right? So you are saying okay, now I'm going to memorization stage, just stop here, just I have learned the concepts enough. Then you should have ideally stopped here, where the validation loss is minimum. And similarly, looking at the accuracy. Now, since if we look at the accuracy, you see the accuracy has not decreased. It has not diminished. Even if the model appears to be overfitting from the loss perspective, from the accuracy perspective, it is not very much overfitting. So that is why our results were not very bad. But in general, it could overfit here as well. And then you will see a curve coming down. So in that case, our output results would have suffered a lot. But in this case, it has not suffered much because, okay, for this reason. So another reason for this is that my accuracy is computed on discrete values, right? My outputs are matching or not matching. Accuracy is computed on discrete values, but loss is computed on continuous values because the categorical cross entropy is a continuous function. The output is a continuous thing. That's why the loss is decreasing uh, immediately, but accuracy is more or less not much affected. Okay. But ideally, we would have stopped somewhere here. Ideally. Anyway, so this was the whole thing. This was our uh, practical application of neural networks for a problem which is digit classification or any classification problem in general. Okay, if you have any questions, you can ask.
Sir, I have question related to GMM and HMM.
Yeah.
Not this. Because I think that we have already spent 20 days in first semester for this project. So, so I'm not getting any difficulty. Sir, my problem is that in GMM, Gaussian mixer model, what we find actually we find the Gaussian parameter of Gaussian mean and variance. Am I right or not?
Yeah, I would suggest that you go back to your open a Python, open a classifier, open a library which has Gaussian mixture model implemented into it, and then you try to use it and try to see what actually happens. So I can tell the theory to you, but just like we did with the neural networks, we actually implemented it with a TensorFlow or Keras utility. You go back to, I think, sklearn, or there are some packages in Python which you can directly use to implement Gaussian mixture models. Maybe I should give it as an assignment. I think let's do some assignment or exams so that we can learn better. I will give one assignment to you so that you can learn this thing. And so this is the thing that GMM basically it gives you probability of, oh no, this does not give you probability of y given c. It gives you probability of x given y. Yeah, probability of x given the class. This is the GMM. So GMM will output what is the probability. So basically each class has a separate GMM. Let us say I have my green class, it will have one GMM. My blue class will have another GMM, red class will have another GMM. So my green GMM, if you put any X input, it will tell you, it will give you a number. Okay, probability that this X belongs to this class, or probability of this class given the x, or sorry, probability of x given this class is, let us say, 0.1 or something. And then you feed that same x into another GMM. It will tell you what is the probability of this x for this particular, coming from this particular class. That will be a small number, 0.001, let us say. Now you give the same x as an input to the red GMM. This GMM will say the probability that this x uh, will be observed in this distribution, that will be even further small, 0.0000001, something like that, which means that it really is a very small number. So this part is the GMM.
Okay, sir. Okay, sir.
And to actually see it, I would suggest you do an assignment. I can give some sample problems or sample assignments which will
Yes,
help
sir.
you
Yes, sir.
to
Yes, sir.
prepare.
Yes, sir. Yes, sir.
Okay. Any other question?
Sir, what is the deadline of the project?
Deadline of the project will be, okay. I will announce it. I will now announce it on the platform. Okay. Okay then. Should we stop here? Okay. Thank you. Bye.